Okay. Welcome everybody to the first monthly meeting of April, excuse me, still a month behind.
He's trying to fool us.
Yeah.
What's that?
An April's Fool joke, right?
April Fool.
Exactly.
So we have some announcements to make first. Oh, this is the Santa Barbara Astronomical Unit, our 7:30 meeting, first Friday of every month. We have an announcement by Chrissy Cook.
Promise to keep it brief. Thank you, Jerry. Two announcements. Number one, I am actively recruiting new planetarium volunteers. We are in desperate need. I have currently just 2 volunteers, and therefore we only have shows 2 days a week, but we could have more shows if we had more presenters. So if you feel the desire to share the incredible wonders of the universe with people on a regular basis, I'm happy to provide training and background information. Please get in touch with me. You can find me at the museum's website, or I think the AU website still has a phone number that'll find me. Additionally, speaking of the planetarium, the museum has approved an upgrade to our planetarium.
Yay!
Yay! All right. Yes.
We will be upgrading to Digistar 7. Very exciting. And they have committed to $1 million capital campaign fund to upgrade the projector to a 4K system, as well as other upgrades to the Space Lab exhibit hall gallery outside the planetarium and structural upgrades in the planetarium itself.
Yay.
So that will be a 2-year capital campaign, and I'm so thrilled to see the museum really throwing its support behind astronomy programming and making sure we're doing lots of cool, fun stuff. With that, I'll bow out. Thank you very much.
Thank you, Chrissy. And now we'll hear from our outreach coordinator on the upcoming events that are scheduled. Chuck.
Okay, we're starting to ramp up public events again. So our first event coming up is actually Thursday, April 7th. So there's typos in the newsletter that just came out, but it's Thursday, April 7th, set up at 6:30 p.m. For Hope School 5th graders, and we set up on the blacktop behind their main buildings. And it's a moon night for them. So it's mainly going to be focused on the moon. And then we have, of course, second Saturday of every month, we have the Star Party at the Museum of Natural History. Set up is at 7 because the latest museum output says that it starts at 8, which is what we thought initially. So so we can maybe have our planning meeting a little bit later. And then coming up on the 3rd Friday of every month, so the 15th, Westmont Public Telescope Night, we set up there. And then there's a couple of events that are still pending, so I won't quite put those up yet. But then coming up, the big event that we're going to have is on the 30th, is the Kaleidoscope camp out, the jamboree that the Girl Scouts have every other year. And at first they were saying it was going to be 500 Girl Scouts, and that grew to 1,000. And now I think it's at around 1,800. So we'll need to grab some volunteers for that. Volunteers are going to, for all our public events, have to be vetted through the museum and have the security check and the proof of vaccination. But for the Girl Scout events, in addition, we have to do a Girl Scout background check. And that's a simple online check. So just contact me at outreach@sbau.org or macpuzzle@west.net. And I will get you the information you need to log on to the Girl Scout system and get your security check with them. And then coming up in May, I got in touch with the big box out there at Camino Real Marketplace. And so we're set for Astronomy Day there on May 7th on Saturday, International Astronomy Day. And also we're going to start Telescope Tuesdays there again every Tuesday, or every first Tuesday of the month. So once a month, Telescope Tuesday at Camino Real Marketplace. And that's in addition to our second Saturday and third Friday events. And we also have possibly a solar viewing event at Westmont on the 16th of May, which we're setting up right now for advanced placement physics students at Santa Barbara High School. So that's kind of the preview of the outreach for this month and next month. And oh, and by the way, we still the current museum direction is still that volunteers should wear masks at all events, indoors or outdoors, when we're dealing with the public. That may change if the rates go down. The rates are currently pretty low, like 3 per 100,000. But we haven't heard direction from the museum about ditching the mask just yet. So make sure you have your mask with you. Thank you.
Thank you, Chuck. And now I'm going to turn the meeting over to our Vice President, Ron Herron, and he will introduce our speaker for this evening.
Okay, we love the club. Santa Barbara Astronomical Unit. Tom Totten doing a great job again. Don't forget our Monday morning podcast. Every Monday, we're about to do another 58th on Monday at 11 a.m. You can watch on YouTube just like now. We got another one, another future Neil deGrasse Tyson on his way into a career of astrophysics, everybody, is our speaker tonight. If you remember last month, since this is our second online meeting after 2 years of pandemic, it was a grad student, a young lady, UCLA, Briley Lynn Lewis, spoke on exoplanets. And this time, I got to tell you, this month, we wanted to pay homage to our local LCO network of observatories around the world. So the director of Las Cumbres Observatories, headquartered in Galita and the UK, Lisa Scory Lombardi, turned me on to this young man you're about to meet, who's going to give us an update and also cover his own take on exoplanets, one of the most prolific areas of astronomy, I might add. And Mr. Totten sent out an email giving the title as LCO and the exoplanets. It's a slightly different title from our guest who we're about to meet. Ladies and gentlemen, future astrophysicist, well, hell, he's one now, and an astronomer on his way. I got to tell you, he's out at UCSB's Department of Physics, grad student last year, I guess, National Science Foundation Graduate Research Fellow, helped develop and maintain a data analysis pipeline for the Galita-based LCO, Las Cumbres Observatories, and a worldwide network, as you well know, of telescopes. Title of Mirek's talk is Weighing Exoplanets by Watching the Star. Ladies and gentlemen, let's hear it from Mirek Brandt, UCSB grad student. Mirek?
Thank you, Ron. That was a very nice introduction. I really appreciate it, and thank you everyone at the SBAU for wanting to have me and for the opportunity to be here. So let me go ahead and share this. So has everyone seen this clearly?
Looks good.
Okay. So yeah, as Ron said, I'll be telling you about how I, in particular, and a lot of other people also, are using a new technique to weigh exoplanets and characterize exoplanets. And this work forms the bulk of my Ph.D. work, but it's not all of it. But it's some of the stuff I think is the most interesting. And I think it's very tractable, and I think it's really cool. And so I'm hoping that I'll be able to convey the main meanings of how we do it and why it's interesting. So as kind of a nice thing, my work kind of picks up well from Riley's great talk on March 4th. And I'm going to start at the exact same place. So she asked, what do you imagine when you think of an exoplanet? And many of you said, a dot. So I have a picture here of the pale blue dot, mountains and gas. So here's an artist's rendition of what one of these odd exoplanets might look like. And some of you even said ocean. So here's an ocean exoplanet. And I guess the way you could boil down my entire talk is I'm trying to show you a complementary way of seeing an exoplanet that actually uses no direct sight of the planet at all. So this is an outline of tonight's talk. So I'll give you a little bit about who I am and the other things that I work on. I'm going to introduce the importance of knowing the mass, so the total weight of these planets. That's one of the things I study the most, and it turns out to be one of the most key properties that we really want to know. I'll talk about why we have a knowledge gap in masses, so we really need more masses. And I'll talk about the technique that I use to weigh these planets and characterize them, which is astrometric accelerations. And that segues into how we're actually using astrometric accelerations to do informed direct imaging surveys of stars. So last month you saw these beautiful pictures of stars orbiting each other, taken on direct imaging instruments. And so we're actually using this technique to inform those instruments of which stars to look at. And then I'll finish with some highlights of LCO's recent research. So I have a lot of interests. I started out in grad school, actually slightly before actually formally starting a student at UCSB, working with Las Cumbres Observatory, and I'm still working with them. But I started out working with them on radial velocities of stars and getting things like how bright the star is in each color, so the spectrum. So here I've just shown a plot of a stellar spectrum taken on Las Cumbres Observatory's network and processed by the data pipeline that I helped develop, which just shows you the brightness of the star at each wavelength. So we use this to study things like how fast the stars are moving away from us or towards us. That work involved a lot of software engineering and data science. And so I learned a lot from the data scientists and software engineers at LCO and learned a lot of their tricks of the trade. And I incorporate a lot of that into my research today. And all of this kind of wraps into how I'm now actually studying and trying to characterize exoplanet systems. So study, how these systems move and what their planets are like and what orbits they're on, how far away they are from the star. And this is all work basically with UCSB, but there's still some conjunction with LCO. So again, my main focus is on characterizing and weighing exoplanets. The picture shown to the right here is one that you may remember from last month's talk. It's a system called HR 8799. So the star here, which you can't see because of how the instrument's set up, is kind of blocked out. But there are these 4 planets that are lumbering off in the distance. It's a very famous system. It's one of the few systems that we've ever imaged that has more than one planet in that image. And consequently, it's really interesting. People spend a lot of time studying it. And one of the works that I'm most proud of is our ability to actually, for the first time, weigh this innermost planet. So that was a paper we published really recently about how we did that. And that's what I hope to describe in broad terms. And I think that will hopefully come across is how we actually did that. Don't know if there are any questions at this point for me.
Not that I see any, Mirek,
Okay.
so please continue.
Great. So part 1 of the talk, I'll talk about why we tried to study the innermost planet and why we tried to get the mass. And part 2 is going to be about how. So the technique we actually use to get this mass. And a little teaser is a picture here of the Gaia space satellite, which is a big part of how we actually do that.
I have a question.
Yeah, go ahead. Please.
On the last slide, the E planet,
Yeah.
How close is that to the star? About the same as Earth is?
It's about 20 AU from the planet.
Okay, that's okay.
Yeah, so it's far. It's
By
on
the way, sorry. Yeah.
No, it's a great question. Yeah, so that will actually tie into why measuring the weight of these planets was pretty difficult and required something like the Gaia space satellite to do.
Okay.
Because it's on such a long period orbit. So yeah,
And what was this picture taken with?
I believe this is Sphere. So it's a direct imager. Yes, I believe this instrument is called Sphere. Yeah.
You said 28 AU?
20. It's about 20-ish. 20
Yes.
AU. Yeah.
You don't know if that's in the Goldilocks zone?
It should be pretty far away from it.
Right.
This star is also would be a bad star to live around because it's very young and it's pulsating and it's much brighter than the sun. But yeah, no, that's a good question. Yeah.
Mirek, I have one other question.
Yeah, go ahead.
On the paper, it says there's a person named Timothy Brandt.
Oh yeah.
Any relation? Any relation?
That is my advisor, and I heard that he has spoke also to you all, but there is no familiar relation. But it is funny that we have the exact same last name. Yeah. Thank you. That's a good question.
Good.
Yeah.
In years, he was a good speaker too.
Oh yeah, Tim. Yeah, I really enjoy Tim's talks. Yeah. Okay, so I'll be focusing on things called brown dwarfs, but in your head, I would just kind of think of them as planets. There's some contention in the community as to whether to consider them planets or in a class of their own, but they're objects that orbit other stars that don't produce a lot of their own light. So they're not stars. They're not burning hydrogen through nuclear fusion. They're not giving off tons of light. And they fall kind of in the intermediary between stars and what are commonly referred to as planets, so rocky planets and so forth. So brown dwarfs, typically they have anywhere from 13 to about 75 times the mass of Jupiter. Exoplanets are anything below 13, and stars are anything above this limit. And so these span a huge range of mass. And consequently, because they span a huge range of mass, they also span a range of different formation mechanisms. So some brown dwarfs are thought to be formed just like planets, so kind of falling to the bridge to the left, and some brown dwarfs are thought to form just like stars. And so studying these is really important because we kind of get 2 for 1. We kind of learn maybe about how planets form and also about how stars can form. So I just want to take a moment and show you some images and also give kind of a question for you to think about and respond. So these are some images from ALMA of protoplanetary disks. You can see these channels carved out in the disk. Those are sometimes planets, sometimes they're not. Sometimes it's just interesting disk physics. But this is just to provide some context for what these disks look like. And these are the material that planets actually form out of. So considering some star with some dusty gas around it, how might planets and brown dwarfs take shape in that environment? What are your thoughts? Can throw anything out.
It looks like in one of those pictures, it's almost forming spiral arms around the disk in the 1M LUP.
Oh yes, yeah, this one.
Yeah.
Yeah, so that's a great point. So yeah, one way that planets can form in these disks is through basically disk instabilities causing things to kind of coalesce.
Do these planetary disks like this, do they orbit like a galaxy does with everything out there moving at the same speed, or do they follow Newtonian?
That is a very good question. That is a very good question. Because these spiral arms are very tightly wrapped, my guess is they're closer to Newtonian than a galactic disk. Yeah. Yeah, it's a good question.
I got a question.
Oh yeah, go ahead.
Question about brown dwarfs.
Yeah.
I hope this isn't off the topic necessarily, but is there any way to know that there are systems out there that feature a super Jupiter that didn't become a star but has got other planets going around it, and could you see it?
Yeah. So
what?
Yes. Yeah. The answer is yes. There are. There's a famous system of isolated brown dwarfs. So there's no star. It's just 2 big brown dwarfs orbiting each other. And certainly planets probably could form in that environment. So yeah, you could have a starless solar system. It's certainly possible. See them. Sorry?
You couldn't see them.
They'd be very dim in the optical, yeah. So you can see them sometimes if you go far into the infrared where they're still warm. But yeah, that's a great point.
But the ones you were talking about were orbiting the stars.
Yes. Yeah.
Okay, gotcha.
Yeah. So one way that planets can form, sort of in the way that Jerry brought up, is that you can have interesting disk physics leading to things collapsing in the disk and forming. Another way is you can have kind of protoplanetary little small cores basically accrete pebbles of material until they grow in mass. So this is an image of a system called PDS 70, and these are 2 brown dwarf-ish planets. They're about 1 Jupiter mass and 5 Jupiter masses. So they're not quite in the brown dwarf territory, but they're large planets that are still in the process of forming and accreting. And you can see they've carved out a huge channel of material. And so kind of a motivating question for me has been, okay, we can look at systems like this that are very young. We can look at what they probably turn into at their old ages. But what is exactly happening with these planets, and how exactly are they forming? Are they forming from a core of rock that's slowly accreting material, or are they just collapsing out of a big cloud of gas like a star would? That's been kind of a driving question behind this entire work.
So Mirek, I would guess that PDS stands for what? Planetary Development System, or
I've not heard that. That's a good one. PDS, I believe. I don't know the origin of the name, but my guess is it's the name of the survey that was used to discover it. That's my guess. So for instance, planets discovered by TESS often are given their TESS designator. So the planet's like TESS 5011b or something. But yeah,
I would guess planetary disk survey.
that might be it actually. Yeah, planetary disk survey, that could definitely be it. Yeah, but I like Tom's suggestions. Maybe I should shoot them an email and see if they'll adopt it. So in trying to answer this question of how exactly do these planets form, it turns out that the mass of the planet is key, and that it's not easy to get the mass. So that's been the focus of my research, is how do we get the mass of these planets? If you have the mass, you unlock two really cool things. You basically immediately learn how old the brown dwarf is, if you also have an image of it. And sometimes you can actually learn exactly how the brown dwarf formed. And so to understand why, we're gonna go to a different model of a brown dwarf, where a brown dwarf is just a cup of coffee orbiting a star. And the physics is very similar. So I'm gonna give you a thought-provoking question here. So the question is called, when was your coffee poured? So a friend comes to you with a cup of coffee that's at 120 degrees. And they tell you it was 200 degrees when it was first poured. And they ask you, how old is my coffee? So can anyone answer that, or is there information missing?
Got to know the rate it's losing heat.
You got to know the rate. Yeah, exactly. That's it. So you got to know the rate it's losing heat. And to know that, you can know it's coffee, but you have to know how much mass there is. Right? If there's a huge amount of mass, it's going to take longer for that, 40-ounce cup of coffee to cool down than a 10-ounce cup of coffee. So that's the key question. So yeah, I mean, you answered it. So the next slide might be kind of redundant, but you need the mass. And so what I've shown here is two cooling curves for a small cup of coffee and a large cup of coffee. So as time goes on, they're going to track down this cooling curve. And all you know is that the temperature is at 120 degrees. So you can't distinguish between a large cup and a small cup. And this is exactly what happens with brown dwarfs, is you have a large brown dwarf and a small brown dwarf, and you know the temperature today. You can't tell how old it is unless you know the mass. And if you know the mass, then everything falls out and you're good. So it's the exact same situation that an old and heavy brown dwarf can sometimes look exactly the same as one that's young and light. So brown dwarfs are just like cups of coffee. They're not all the same mass. And so we have this so-called degeneracy, that we can look at two brown dwarfs and not know how old they are, unless we know the mass. Are there any questions on that?
Are you going to give us weights? The title of your talk is The Weighing.
Yeah, the weight. Yeah, so we'll get to that.
Oh, okay.
Yeah. So to establish, this is all to establish, why do we care about the mass? So it turns out that knowing the mass gives you the age. The second question is, well, how do these brown dwarfs form? So I'm going to give another coffee analogy here. So this one's called, where did your coffee come from? So we're going to consider two formation scenarios of your coffee. So one is going to be the McDonald's hot start. And you all know at McDonald's, you get your coffee and it's like too hot to drink, 200 degrees Fahrenheit. The second one is your local coffee shop cold start. And it's served at, let's say, 110 degrees Fahrenheit. But this time you're told, I was poured this coffee an hour ago and it's temperature right now. So again, I think the answer is it's going to be the same answer, but how do you know, what extra piece of information can you be given to know which coffee shop it came from, whether it was a hot start or a cold start?
Mirek, I got to ask a question.
Yeah.
What about surface area? How does that relate to mass somehow, or?
Yeah, so this is a great question. So yeah, in real life with coffee, I'm glad you asked this. In real life with coffee,
actually, this kind of a question or a comment put up by Sean Kelly. He's watching the program.
Oh, excellent. So. Okay, well that is a great question, Sean. So coffee, as you know, right? If you have a bigger coffee, more mass, it's going to be bigger in surface area also. But brown dwarfs have a very interesting property that if you increase their mass, they have almost the exact same surface area. It's very weird. It's called degenerate electron physics. So actually, a heavier brown dwarf is actually slightly smaller than a lighter brown dwarf, but they have almost the same surface area, which is why this problem is so hard. That's a great question.
How do you get the size of these things? Do you do it by occultation?
You may be able to do that. A lot of brown dwarfs that we have imaged are really far out, and so it's very unlikely they actually pass in front of the star.
Yeah.
We haven't found one yet. A typical way to get the radius is to know how bright it is and how heavy it is. And from that, if you know how heavy it is, you can basically construct a model. So you have to rely on these complex physics models. You construct a model of how big it should be. And then given the brightness and the temperature, you can go back and get the radius.
So it's a derived quantity.
Yeah, it'd be a derived quantity, yeah. It'd be hard to measure on these things physically. If we could, that would be amazing. If we found a brown dwarf that was passing directly in front of its star, that would be amazing. These are great questions.
Yeah, and if it is a brown dwarf orbiting a star, you could get transits, which is similar to the occultation.
Yeah, no, totally, yeah. So that would be a transiting brown dwarf would be like a gold mine. And the reason it's unlikely is just geometric. It's just so, these imaged brown dwarfs are so far away that it's really unlikely for these two things to line up. Yeah.
How much bigger than Jupiter does a gas planet have to get before it lights up?
If you get beyond about 80 Jupiter masses.
Oh, 80.
Yeah, 80, then it will begin to fuse. And the exact position of that boundary is a little bit debated, but it's around 80.
Okay.
And one more question about brown dwarfs,
Yeah.
Sean, is how can brown dwarfs have solid cores?
That is a good question that I do not know the answer to. That's a great question.
I think they've discovered what Jupiter is kind of the core is not necessarily one blob. It could be kind of multiple blobs around in the core. Is that true, Chuck?
I don't think it's multiple blobs, but I think it is diffuse rather than a nice solid thing. And same for Saturn.
Yeah. Yeah, these are great. These are great questions. I wish I knew the answer. Yeah.
Just thinking about the woman who sued McDonald's for the coffee that spilled in her lap.
Yeah.
They dimmed it.
Sued over a brown dwarf.
Yeah, right.
Yeah. So anyway, just kind of glossing over this a little bit. If you have a temperature and age, so they told you it's an hour old and it's now 78 degrees Fahrenheit, you don't know whether it came from a large cup from the local coffee shop or a small cup from McDonald's that was super hot. And this is the exact same problem with brown dwarfs when they're young. But if you know the mass, then you can immediately pick it out. So if we know the mass, then we get the age and the formation history. So that's why the mass is just so key, because it tells us how these things formed. So the reason I use the hot start and cold start analogies for McDonald's and your local coffee shop is because these are actually two mechanisms for how brown dwarfs form. It's cold start and hot start. It's just how they're named. And they're extremely hard to tell apart unless you know the mass, and then you're good.
What is a hot start?
So a hot start is you just have a cloud of gas and it's so big that it starts to collapse. And that's it. It just collapses and forms a brown dwarf. That's all a hot start is.
So that's gravitational collapse that makes the heat.
Yeah, exactly. It's all the heat gravitational collapse.
That was what I assumed was a cold start.
Yeah, so a cold, yeah, I had the same question about this. So a hot start is when you have all that gravitational collapse energy, and that's it. It's just simple. A cold start is when you have the same scenario, stuff's infalling, and when it gets to a certain radius, a certain compactness, it actually starts to form a shock. So it kind of, a really dense region that's emitting a lot of light, and it's actually radiating away a lot of heat. So it's cooling down.
Hmm.
Now,
and so that you lose some of this heat of formation. Yeah.
So that's going to depend on what it's made out of, whether it does a hot start or a cold start.
Yes. Yeah. It's a great. Yeah. It's a great comment. Yeah.
Yeah, and some brown dwarfs have lithium and do a brief period of lithium fusion. So wouldn't that kind of mess things up?
Yeah, exactly right. Which is why that's one reason why this limit of 13 Jupiters is chosen, because beyond that, then you almost always fuse deuterium. But yeah, you're exactly right. If you're right below, then you don't, and if you're right above, then you do, and the object actually gets a little burst of brightness, and so it complicates this picture. It's as if you got poured a cup of coffee, and then 20 minutes after pouring it, like a heating pad went off in the coffee and reheated a little bit. It's going to mess up your calculation of how old it is. That's a very good point. Okay, so these questions are great. I really appreciate them, by the way. So keep them coming. So once we have a mass, we can measure the age, and if the planet's young, we can actually ask, how it's formed. This McDonald's versus the local shop question. So that tells us everything. I mean, and how these brown dwarfs formed and where they formed, because they're so massive, can tell us about how the solar system it's embedded in has evolved. So it can tell us not just about that one planet, but possibly about how things came to be. Sort of like how we've learned so much about how our solar system has evolved based off of the evolution of Jupiter. So masses give us so much, but we have so few of them. So this is the current state of astronomy right now, and we're really trying to get more of these. So just to give you some numbers, there are about 5,000 known exoplanets, and there are about 100 brown dwarfs, and only about 20 of those 100 are both imaged and have a known mass. And so, I mean, there's not much you can really do with, a statistics of 20. It's hard. And so this is where we're really trying to pump this number up. So yeah, we need to build the sample size up. So that's what my entire research is focused on, is building this sample size up. So how do we measure mass? So now we're getting to this. Now we're going to talk about weighing the planet by watching the star. So as Briley talked about in her talk, a lot of these systems look like this. And so you look down here, and this ticker is going over about 10 years. And these planets are moving just a little bit. So we don't really know super well what their orbits are. In this particular case, there's complementary data that we actually do know these orbits pretty well. But for a lot of these systems, we have such a little orbital arc that we don't really know the orbits well. If you don't know the orbits well, then it's hard to get the mass from traditional methods. So that's where we're going to turn to this new-ish method that I focus on. So, I mean, in a nutshell, watching the star move across the sky can tell us the mass. So I have some images here of Barnard's star, which does not have a brown dwarf around it. It does have a planet around it, but it's a small planet. And it's moving like how most stars move across the sky, which is just a linear path. So here you can see actually Barnard's star is one of the I think it is the fastest moving star in the sky. And it moves a significant amount between 2004 and 2008. So here's another image of this from a different telescope, and it actually shows more years of the star moving. And so we're going to move away from these images here to a more plot representation. So all these little red crosses mean is this is the star's position at 1991. Here it is, a couple of years later, moving up the sky. And this is in your familiar DEC and RA. So keep this when you see this image, you're actually looking at position of the star. So now I want to look at a different star, and you'll notice immediately that its sky path is not straight. So between 2015 and 2019, it's moving on this weird curve. So what are some thoughts of what's going on here?
It has a big exoplanet dragging it somehow.
Yeah, that's it. Yeah, exactly. Great. Yeah, there's a big exoplanet dragging it. And so I'm going to describe this. So if you look at this mysterious planet or mysterious star in its own frame of reference, the center of mass stays fixed, and the planet or the star and the planet are just orbiting each other. They're dragging each other around. It's like two ballerinas that are slight, one's heavier than the other. But we never look at a star in its own frame of reference. We're on the Earth, and the star has some velocity. The center of mass has some velocity to move in the sky. So imagine taking this entire frame, this entire orbiting thing, and moving it to the right. So that's what we're going to see here. Is all I've done is just shift this entire thing through time, moving it. And you can start to see this weird path being shaped out.
Uh-huh.
So there's an extra complication. We don't see the planet, right? All we see is the star. So we look up at the sky and we just see the stars doing something weird. And so this is what I mean by how we can weigh planets by just watching the star, is because a more massive planet is going to tug this thing bigger, and a less massive planet is going to tug this thing on a shorter arc.
So it's Gaia that's giving you the milliarc seconds that let you do that?
Yes, exactly. Yeah. Yeah. No, that's a great point. Yeah. Milliarc seconds, you can't do this on the ground, obviously. So you need space telescopes.
Well, are there other planets?
Yes, there's tons of them, and there's more coming, which I'll get to in the end. So I'm hoping to excite.
I meant around this star.
Around this star? So
yeah.
This star is actually fictitious, but it's designed for this purpose. Yeah.
Okay, gotcha.
Yeah. This is something I designed for this talk. It's just a fake planet that would really emphasize this effect. Yeah. But there are plenty of things that are like this.
Oh.
Yeah. So this is how we see a planet without seeing it at all, is we look for stars that are doing this, that are having a weird sky path. And the cool thing is that we can actually back out the mass of the planet basically by trial and error. You put in an orbit you think the planet might be on and see, does it match? Does it affect the star in the way that we see? And you just keep trying it millions and millions of times. That's what these advanced codes are basically doing.
So Mirek, you have to know the mass of the star, right?
Yes, yeah. So you can get the mass of the star from stellar evolution, or if you have enough complementary data, so not just the sky path, but you have things called radio velocities and this direct imaging, then there's actually a way to get both the mass of the star and the mass of the planet at the same time. But just naively, if we just have this motion, then we do need to know the mass of the star beforehand. That's a great question. Yeah. So yeah, I'm giving I guess a more quick run through, but yeah, there are these great complications like what Tom just pointed out. When you actually do the analysis, there's some things you need to deal with. So I'm just going to do the simplest case of what these codes would basically do, which is you have some observed sky path, and this white curve here is the model at varying masses. So I've just varied the model between having a planet of mass 0 and mass 300 Jupiters here. And so just staring at this, I mean, what does it seem like to everyone that the mass of the planet is? Might be kind of hard to catch the numbers, but a ballpark answer.
Looked 120-ish.
Yeah, yeah, great. Yeah, excellent answer. Yeah, so it's around there. And that's basically what we're doing, is you have the sky path.
So that's not a brown dwarf then, that's a star.
Yeah, so again, to emphasize, that's a great point. To emphasize this effect, I've made the planet more massive than it could ever possibly be. But you can have the same thing for a smaller planet, and this scale of this effect in milliarc seconds will just be smaller. But yeah, and really this would be a star. Yeah.
Well, it could be a black hole, right?
Yeah, you could have a small black hole, sure. Yeah. Yeah, that's a good point. So yeah, if we saw an effect this large and we didn't see the companion that was doing it, that would be pretty good evidence for some kind of dark companion.
You said that a brown dwarf lights up at about 80 Jupiters. At what number does it become a brown dwarf? Jupiter is not a brown dwarf, is it?
No, Jupiter it shares a lot of the same physics. So a brown dwarf is actually a similar size to Jupiter, like in terms of like visual size in the sky.
Yeah, well, if you ever saw the stupid, dumb sequel to 2001, it was called 2010.
I never actually saw the sequel.
Oh, well, don't, because they light up.
Okay. I'll refrain from doing that. Yeah.
Roy Scheider played Dr. Floyd. Far out.
So, I mean, basically the name of the game is you have these observed sky paths and you can fit a range of planet masses to them. And so, 120 was called out. That's basically right in the range it would be. And again, sorry, go ahead.
Oh, since you brought up Jupiter, and it's not a brown dwarf, Jupiter does emit more radiation than it receives from the sun. And so in the infrared, you can take pictures of it and you can see the emission coming through the bands.
Yeah, if you had a precise enough telescope, you could image Jupiter.
Yeah, but will Jupiter ever cool off? Will it ever lose that ability to emit?
So Jupiter is in many ways much like a brown dwarf in the sense that it's basically just cooling, like a cup of coffee. It's already super hard to image a Jupiter-like planet. So I believe that the James Webb Space Telescope is still not precise enough to image a Jupiter-like planet. But if you dialed back the clock, so you made our solar system, you went back in time when our solar system was 100 million years old, Jupiter would be bright enough then to image.
Okay.
It'd be so hot.
Thank you.
Yeah, that's a great question. Yeah. Okay, so that's how we weigh planets with this method. And the next question, which is getting to the end of the talk, is, well, if we can weigh planets, what about detecting them? And this is where Hipparcos and Gaia really come in, because they've looked at so many stars. So here I've shown the Hipparcos satellite, which flew in the 90s, and here's Gaia, which is flying right now. So the way I would think about why this is so powerful is, imagine this planet, instead of being 4 years, it was on a 30-year or a 40-year orbit. You have Hipparcos observing it 30 years ago from today. So you have this big lever arm. And whenever you have data, you have huge lever arms, separations in time, you really gain a lot of constraining power. So by combining these two data sets, you get a lot of power to measure these planet masses. So going back to the beginning of the talk and also kind of tying into what Bradley talked about is, imagine that we didn't know that HR 8799 hosted any planets at all. Just imagine that we didn't get lucky and we didn't look at this planet. We didn't see it. With this new technique, we would have known, actually, as of 2020, this star would have shown up on the weirdly moving star list and the accelerating star list. So we would have had a reason to go look at it. And so we can detect new planetary systems. That's what we're doing right now at UCSB, is actually going through lists of stars that are accelerating and looking at them. So recall from her talk about direct imaging that if you just blindly look at stars in the sky, you have about a 0.5% chance of finding a imageable planet. If you look at these accelerators, it jumps to about 10%, so about 20 times higher. So that's the power of this survey, of looking at stars first and then going in with that information and looking for planets. And if you want to know what the chances of just finding not only planets, but also stellar companions, so a low mass star. So that example I gave with the 120 Jupiter mass planet, that would be a great example for this, is you might find that it's a star, not a planet, but it's just so dim you didn't see it before. That's about 33%. So we've gone from 0.5% to basically 1 in 3 things we look at are positives using this method, which is exciting. I mean, this is like the new era of direct imaging.
Mirek, why do you call it an accelerator? Those telescopes, or you consider them accelerators?
I consider I would say the stars are accelerators. If stars that have sky paths that look like this, I would say is an accelerator. The satellite looking at them is Gaia and Hipparcos. So if this star was instead going on a straight path, it'd be a non-accelerator.
Okay, thank you.
Yeah.
Basically, if something is accelerating it transverse to a straight path.
Yeah.
They're really moving? I swear they don't change places when I look.
Yeah, when you're talking about Gaia milliarc seconds, then yeah, these things move. So this is about a 50 milliarc second shift.
Oh,
When you talk about a 2 Jupiter mass thing instead of 120, then you're talking about a 1 milliarc second effect. So it's really small. Yeah. So do this. And so I think a good place to end this portion of the talk is to say that more discoveries are coming really soon. So when I just said we were going through this catalog of accelerators, every star we said, okay, we just sort by the most weird moving stars and we look at them. We had about 10,000 or so. In a few months, Gaia is actually going to release 800,000 stars that are accelerating. So many of these will be binary stars. They won't be really that interesting to us, but some fraction of these 800,000 are going to have new, yet undiscovered planets and brown dwarfs. So this is in a few months. It's just coming. So we're really going to have our work cut out for us.
Mirek, how far out are they? Do you think they'll be seeing any movement of stars? How far away, light years, or does it depend on the size of the star? Or?
No, that's a great point. So we are restricted to stars that are close by-ish. So things that are probably closer than 100 parsecs, so 300 light years. And the reason is the further away we get that the planet or the star gets, the smaller this effect is. It scales in the parallax, basically.
But 800,000 means it must be reaching farther than 300 light years, right?
Let's see. So the galaxy is 100 billion stars and 8 kiloparsecs. So I think that works out. Yeah, I think there's probably that many stars in 300 parsecs. Is my guess.
Yeah.
Wow,
it's reasonable.
okay.
That checks out, Jerry.
Yeah, no,
Okay,
I'm just doing the same mental thing you are.
Okay, great. All right, I'm glad that checks out. I wasn't 100% sure. Yeah, yeah, it kind of is a mind-boggling figure that there's 800,000 stars that close. That's wild.
Yes.
A couple of globular clusters.
Yeah, I get to do it. Yeah, that's a great question, Tom. Thank you. I really appreciate that until now. Okay, so I'm going to move into other exciting science. Just a really brief kind of tip of the iceberg look into LCO. So LCO is, again, Las Cumbres Observatory based in Santa Barbara, but global telescopes all around the world. They produce lots of data, lots of collaborators using the network. There's about 1,000 peer-reviewed papers using LCO data, and that's mostly from data from the last 8-ish years or something. So you're talking about 100 papers a year from one observatory, which is pretty awesome. And you can actually browse the list of publications that come out using any type of LCO data. So this is just an example. One really exciting thing that just came out, which is actually led by another grad student who just graduated, they're just now going on to a postdoc, Daichi, who discovered the first observational evidence of something theorized for a long time. So when you have big massive stars, between about a solar mass and 8 solar masses, they collapse in a well-known way. And when you have stars that are more massive than about 10 solar masses, they collapse in a well-known way. But there was this gap between 8 and 10 solar masses that people didn't really understand. People had theorized that this thing called an electron capture supernova would happen in that range, but they'd never seen it before. And so LCO and Daichi were the first people to actually observe this phenomenon. And I'm sure you all recognize and Andy there as a familiar face. So this is like the big headliner, but there's also other cool science going on. So Tim Lister at LCO is part of the DART team. So the satellite that's going to actually trying to redirect a asteroid just for a test to see how well we can do it. So he's working on following up on to actually observe this asteroid after it's been hit. Rachel Street and collaborators, they've worked on the discovery of the first, I believe, wandering black hole just through our galaxy that just happened to pass in front of a star. There's also some really cool work with magnetic fields and hotspots in young stars. It's not with people directly at LCO, but it uses LCO data. Yeah. So there's really exciting stuff going on at LCO all the time.
Very exciting.
Yeah, thank you. So with that, I'll end there. Thank you. I appreciate everyone listening. I'm sure it was the information overload of a talk, but wanted to get through everything. So yeah, I'll take any questions if there are any. And again, thank you for having me.
Well, Mirek, your specialty then is those trails of the stars that are going up and down. You don't ever deal with the occultation, dimming of a star when we see it on edge. That's out of your field of expertise.
Yeah, I don't deal particularly with transiting exoplanets. I've done a little bit of work with them on the side, but it's not my field of expertise for sure. Yeah.
I got you.
Yeah.
Well, that's fascinating stuff. You don't think the James Webb will be able to detect any of that infrared off the exoplanets?
James Webb, that is a good question. I believe that James Webb will probably not discover any new transiting exoplanets because it's a narrow field. It's looking at one star, but it's going to be really valuable for doing follow-ups of planets we know are occulting and transiting to get their spectral in the transiting. Yeah, it's going to be really valuable for that.
And then deep space, early galaxies, way out there.
Oh yeah, that's going to be amazing. That's going to be.
Any other questions?
Yeah, Sean Kelly wanted to bring up that the Gaia mission evidently can resolve down to millionths of an arc second. Does that sound right?
Yes, it should be. Yeah, the end mission precision on some of the parallaxes should be in the micro arc second range. Yeah,
Wow.
so it's amazing. Yeah, thank you for bringing that up, Sean. That's a good point.
You said you had DART up there for a second. What did you do with that? How did you help NASA on DART?
Oh, so that's not something I'm directly related to, but Tim Lister is part of a team. So Tim Lister is a scientist at LCO. He's part of the team that is doing follow-up of the orbit of the asteroid after it's been hit. So this DART has a bunch of observatories throughout the world that are going to contribute to this effort to track the asteroid's orbit afterwards.
I saw a video on YouTube about an 800-pound satellite or something that we crashed into a big asteroid 10, 12 years ago. Mr. Prez or Chuck, do you know what I'm talking about?
That was the comet crash.
Yeah.
Oh,
That was a comet. That's right. It was. We couldn't have measured that. Probably didn't make any difference. It was too big. It wouldn't have. If we thought about it, we could watch and see if we maybe altered that course.
Actually, Gary and I watched that from our backyard.
oh wow.
Amateur telescope trying to detect the brightness change of the satellite, and we convinced ourselves that we may have seen it visually.
Oh wow.
So,
Yeah, there were a bunch of us up at West Camino Cielo that were watching it too. And, 15 minutes or so after the event, everybody was sort of convinced that you could see a difference in the view.
Yeah.
Wow.
And
I noticed LCO is restarting the Astronomy on Tap down on Lower State Street. And they
At the
mentioned
Matrix?
Yair. Is Yair coming back or is he still in Tel Aviv?
I believe Yair is a professor now in Tel Aviv, but I think that he comes back somewhat frequently. So I could imagine him coming back and doing it.
Okay,
Astro
thanks.
Talk. Yeah.
wow.
Well, we have one more comment, Ron, from Chrissy Cook. She says, "Great talk. I've never enjoyed McDonald's coffee more."
Thank you, Chrissy. Yeah.
Well, Mirek, when do you think you'll get your doctorate?
It'll be at the end of next year, so about 1 year flat.
Okay, so you're in your third year, and do you get 3, 4, 5? How many?
I'm in the end of my 4th year currently, and 5 is when I'm planning on ending.
I was talking about the professors you got to deal with besides Brandt.
Oh, let's see. I work mostly with Tim Brandt, but I've done a lot of work with the people at LCO. So Curtis McCauley, I worked very closely with. He taught me a lot of the ropes of software engineering. Yeah, so I work with him. I like to collaborate with a lot of people. Yeah. Besides
the lady in charge of the club, your club, Las Cumbres Observatories. We're talking Lisa.
Yeah.
Story. Who was the other lady that she suggested we may have in here in a few months besides you?
Oh, I wasn't giving any names, so I don't know.
Oh,
But I'm sure
That was
she'll be
Rachel,
good.
I think. Rachel Street.
Oh, she'd be awesome. Yeah.
great. Okay. I didn't
Awesome.
even call her. I chose you over. Anyway, we're going to have you back.
Okay. Thank you.
Next
Okay.
month, we're going to feature an astronomer from Caltech, Dr. Ben Darvish, friend of Joe Doyle, is going to speak on the evolution of galaxies. It'll be on
good.
Friday night, the May 6th. And you keep in touch with us, Mr. Brandt.
I will. Thank you very much.
You did
So
good.
let me tell you, Mirek, that that was an excellent talk.
Oh, thank you. I really
And
appreciate it.
your aiming, the visual aids and the aiming at the public level was perfect.
Thank you. I really
So I
appreciate
think it's
it.
going to be a very popular show.
Thank you.
Good job.
You live in Los Angeles?
I do. Yeah. I moved to Los Angeles with my
And
fiance.
commute up here to the University of
I
Caltech?
do. Yeah. I commute. Yeah. Once a week. But yeah.
You're going to need that honorarium we're going to send you.
I really appreciate it. Thank you.
Prices are crazy.
Yeah.
All right, Mr. President, thank you very much for gathering us together.
Okay.
You close out.
Thank you.
Thank you very
Anything else,
much.
Okay.
Tom?
In the meeting for all. Good night, everyone.
Thanks,
Okay.